Okay, so now let us recall what we have been doing. So we are talking about the statistics part, and here we started talking about a population. So you can consider this population as a set of data points, or this is your data set. But this data point, let's say it is a number for the time being. Okay, these are all numbers. But these numbers are produced to measure something, right? Whatever analysis you want to do, whatever experiment you want to do. Okay, so there is an underlying experiment, and this data is produced by measuring something. So whenever we say by measuring something, these are the observed data points, we associate with a random variable. Okay, so this is defined by a random variable. Okay, now so there is a random variable which we consider like it's a population random variable, something like that. But we also consider that sometimes this population is large. So and it's a never-ending process. Let's say if you are working about something like which is a never-ending process, like we talked about an example producing, let's say, lithium batteries, which are used for pocket calculators. So the batteries we talked about, so they are produced in a similar fashion, using a similar technique, using a similar technology. So so they should have this assumption is that they should have the same or similar, let's say, lifespan. Okay, let's say a battery, okay, will be will be working, let's say, for 2 years or for, let's say, 1.5 years, something like that. So now what we want to do is we want to give the consumers, let's say, a so when somebody's company is selling something, let's say, this is a very bad example. You may think about that. Okay, this kind of a situation. Okay, maybe we are at a little advanced stage, so this kind of situation will never occur. But let's say, let us assume that, okay, that, or maybe let's say somebody wants to produce a Bollywood movie. Okay, now the producer, let's say, suppose he thinks, okay, let us consider some of the Bollywood, because he wants to make a profit, let's say. So let us see like what are the observations we can make about the movies, okay, which have made a lot of profit. Okay, so based on some statistics, okay, so she wants to produce a movie such that those ingredients, those masalas should be there in that movie so that it will be a successful. Successful in terms of business. Okay, so it will be a successful movie in terms of profit. Okay, so whatever it is. So, but the thing is, it is population is so large that in that situation you cannot watch all the movies. Okay, and you can find out. So it is a difficult task, let's say, because the population is large. So what you do probably is, the idea is that you take a sample. Okay, and this sample, we said it's like 5% of the population, approximately up to 5%, let's say, and this should be a random sample. So random sample. Now, for the case of battery, at least, so if there are n such sample points, okay, so here the sample point is different in the sense of let's say the sampled points. Okay, so let's say 1 to up to n, they are the sample points, and then we can associate the same random variable x1, x2, dot 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 xn. So for the case of battery, let's say this is measuring the lifespan. This is measuring the lifespan. For the case of movies, so what are the properties does this x1 have? Okay, xn have, something like this. So ultimately, end of the day, you have to deal with numbers. So this is our realization after talking about so many things about probability and statistics, that everything has to boil down to the concept of numbers. Okay, that was the idea of random variable basically. So whatever the experiment it is a biological experiment, physical experiment, whatever it is, or human experiment, everything you have to expressed in terms of numbers. Okay, and in the quantum information theory, so like the Shannon said, Claude Shannon, who is nowadays known as the father of information, that whatever we are doing today, all this digitalization of information, let's say. So his idea was, okay, so information has to be expressed in terms of whatever we are producing, that has to be expressed in terms of a random variable. And whatever the content is that we want to share, that we want to process, has to be digitalized. Okay, that's why we have this laptop, iPad, whatever it is, all the communication systems based on this fundamental principle that everything has to be talked about in terms of random variable and digitalization of some relations about those random variables. So here, in a broad sense, we are doing statistics, not exactly information theory. So here we have x1, x2, xn, and we said that this sample, these are random variables, and we call it a random sample, and these random variables have to be independent. Okay. In fact, since we assume that this xi is, okay, they must have a similar distribution as the x is, so they are IID. So independent, dependent, and identically distributed. Identically distributed. Okay, so we have a situation like this, distributed. Okay, so these are called IID. IID. So these are the IIDs. Now, what is the goal? The goal is, okay, using this x1, x2, xn. So once you, let's say, if you talk about the battery, so we'll talk about this today, that you can have a realization about the value of x1, meaning, so suppose you pick a battery, then it will, you study its lifespan, it will be some number. It will be a number. For x2, the second battery will have a number. For xn, the nth battery, you have a number. Of course, if you take a different sample, so those relations can be considered at x1, x2, dot, 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 x. So these are the values, okay, for the first battery, for the second battery, for the nth battery. But anyway, so it depends on the number. This small x1, small x2, small xn, which measure, let's say, which are the, let's say, the lifespan of this n batteries, which are in the sample, okay. But these are also arbitrary. Arbitrary in a sense that whatever the batteries are there in the sample, based on that, I will get these numbers, x1, x2, xn. So this is just a realization of one subsample, let's say. So the question is now, based on these data points, okay, or treating this as IIDs, can I define something, okay, which can help me, okay, or which can enable me to talk about the entire population. Okay, for example, if I take this particular sample, okay, I can calculate its mean. I can calculate mean of these numbers, small x and small x, small xn, or the variance of these numbers, x small x and small x, and so on. So this is just a symbol. So if you treat that as a random variable, the question is, if you take the sample mean or the sample variance defined in terms of these random variables, okay, do they give us, okay, any clue about the population mean and the population variance? Okay, population mean. So population mean means what? Like whatever the objects are there in the entire population, I'm talking about mean of that without testing or without accessing all these objects individually. I'm just accessing a part of it, a portion of it, and using the data, this sample points, I'm trying to make some conclusion about the population. This could be population mean, population variance, whatever it is, okay, some parameter regarding the population. Now for that, what we said is we talked about two new random variables, which we call sample mean, and the sample variance. Now, in fact, we did not define exactly this as a variance. These are, of course, random variables, but we call it as statistic. Statistic. So in the plural, so it can be called as statistics about the samples. So what is a statistic now? A statistic is nothing but a function of this capital X1, capital X2, capital Xn. Okay, here we define a 1 by n sum over all xi, and here we define 1 by n minus 1 sum over xi. So if we write this as x bar, so this xi minus x bar whole square. Okay, so this as functions, okay, of this capital Xi's. Okay, now the question is for the real scenario. So if you are working in a company or you are in a position, okay, where you need to analyze the data. Of course, the data, suppose it is accessible to you, but you do not know the distribution of each of this, how these data are produced. You do not know that. And of course, you will see in a real situation that later on that there are uncertainties about how the data is obtained. Okay, how the data is obtained. Meaning, suppose they are following a particular procedure, but there can also be uncertainties. Meaning, these data points need not also be exact. Okay, somehow these data points are given to you, but let us forget for that. Let us forget that for the time being. I will assume that this is the exact data, but sometimes what will happen is this data is also not exact. Somehow it will approximate the true value. Okay, what is expected, the true value you are not getting, but you are getting an approximate values of whatever is measured, whatever are being measured. Okay, so so the idea here is somehow you have some random sample, okay, and then you have to make some conclusion. Okay, now since you do not know that how is a distribution of x, okay, so you do not know the distribution of xi's, capital Xi's, you do not know that. Now what we are doing here in a classroom situation, so there is a big difference between classroom situation and a real experience. Okay, so yeah, so what you do given a problem in a situation can be completely different from whatever you are doing in a class. Okay, because maybe there are so many uncertainties that whatever you are learning in this course, let's say, nothing is applicable there. It can also happen. Okay, because here we are talking about in an idealistic situation. We are talking about some theory. Okay, whatever some people have observed. That's how theory builds. Okay, so it is not enough. It is never enough to develop a theory, okay, which will work for all possible situations. It is never possible. Okay, it will of course give you some insights, okay, but it is not all. Okay, so what we are doing here now, okay, we are saying that if x, suppose we know what is the distribution x. Okay, so what are the distribution of, let's say, x1, x2, xn. Then what is the distribution of sample mean and sample variance? This is what we are doing. That means so we are trying to observe if we know the distribution of capital X or the capital Xi, then what is the distribution, or so what is the sample mean of these statistics, like mean of the sample mean of the sample variance, variance of the sample mean, variance of the sample variance, and so on. Okay. So the idea is using those, we somehow can have this idea of mean of the sample mean, or the mean of the sample variance. Can we say something about the population mean? Okay, and we have assumed that when this x is this capital X, the population random variable, let's say, if this is normal, and this is what we have studied in most of the situations, that if capital X is, let's say, normal, or let's say standard normal, or let's say x1, x2, xn, they are obtained from a normal population. So xi's are independent normal random variables, let's say. Then what is the distribution of sample mean, and what is the distribution of sample variance, and what is the mean of the sample mean, what is the mean of the sample variance, and so on. Okay, some parameters associated with this new random variable are so-called statistics. Okay, this is what we have been doing basically. Okay, so now we want to, so now what we want to do is, like, okay, maybe what could happen. You see, the thing is, this has a meaning. It is not just any random variable. Okay, this has a meaning. When you say xi, suppose xi is measuring something. Okay, something like it's a win or loss. Okay, then sum over xi means, let's say, that could be like total number of heads among n. It could happen like this. Okay, so it is not arbitrary. It has a meaning. Okay, so it depends on the situation. It depends on the situation, like what kind of functions I need to analyze, let's say. Okay, so depending on a given problem, okay, this this 1 by n xi's or 1 by n minus 1 xi minus x bar whole square. So basically, this is the error. You can say like this. Error means how much xi far from x bar. Okay, something like this, and the total error. Okay. So the thing is, depending on a context, you may have other characteristics, other statistics, other kind of functions, okay, which you need to analyze to say something about the population. So we have to talk about a general framework. These are examples, of course. Now, these are good examples. Good example in the sense we have observed. We have seen weak law of large numbers. We have discussed a little bit about strong law of large numbers. We have talked about CLT. The central limit theorem. Okay, there we have seen that normal is important. Okay, normal is important. That is what we have seen. So, yeah. No, so we start with any, let's say, distribution. Does not matter. Then we have seen that if we can create the standardized version, and then we have seen that is normal when n is very, very large. So we talked about that. So these are all important things. It is not like, this is a very basic thing, but these are all important things. Unless we know this, okay, we may not even begin to understand how to perform a data analysis. Basically, this is not enough, but this is the beginning. Okay, this is the beginning. So we need to now extend our let's say idea of the statistics. Okay, so instead of the sample mean and sample variance, I can define any statistic. So let me define now in terms of mathematics what is a statistic. Okay, now there are two things. When I talk about this random variables x1, the sample x1, x2 dot xn, so they must be they have some distribution, let's say x. Okay, so they are all IID, and the distribution is like distribution of capital X. Now, whatever the distribution is, whatever we talked about in this course, all the special kind of distributions, let us assume these are all continuous distributions. So they have certain parameters. So whenever we define PDF, the density function, okay, so there is of course a parameter. So whether you talk about gamma, okay, beta, exponential, Poisson, although it is discrete, let's say, okay, so any kind of normal, so any kind of a distribution, there is a parameter associated with it. And these values, when you define this PDF effects, okay, so x is belonging to certain range. It could be minus infinity to infinity, depending on what the distribution you talk about. Maybe positive, or maybe only an interval, and so on. So there are two things in. One is x, which is the parameter, how we define the function. And there are certain constants, which could be arbitrary. Let's say normal. So for normal is defined using mu and sigma square. They are fixed numbers. But when you define it, this mu and sigma square could be arbitrary also. So let's say sigma square is positive and mu is a real number. So they are arbitrary but fixed. Okay, there are two things in mathematics. Okay, one is called arbitrary, but once you choose that arbitrary number, that becomes fixed. So these are arbitrary but fixed. Arbitrary but fixed means you can choose anything. Let's say mu, I can choose 1, I can choose 2, I can choose 10, I can choose 500, I can choose -1. Doesn't matter. It could be anything, but once you choose that, it becomes fixed. Okay, so there are certain parameters which are arbitrary but fixed. Because once you fix that, then only you plot the curve, then only you get the distribution. Okay. So something is normal. If I say, then it is not. There is certain mean. Okay, there is a variance. According to that, it is normal. Let's say. So arbitrary but fixed. There are arbitrary parameters but fixed, depending on what are the meaning of like sigma squared is positive here and so on. We'll talk about that today a little bit. What is about this parameter? But anyway, so it is universally or globally true that when you talk about this density function, we always talk about a class of functions, and there is a parameter involved, okay, in the PDF. So let us denote this as theta. Theta, I'm writing just one parameter. It could be a vector. Vector means there are 2 parameters, 3 parameters, 4 parameters. Like in the case of normal, I have 2 parameters, okay. And in the case of exponential, let's say, so I have 1 parameter, something like that. So, so there is a parameter theta, and there is a function. There is a variable corresponding to the function. Then I say the statistic. What is a statistic? Statistic, okay, is the statistics is a function any function basically. I mean, for the time you can treat it as any function. Any function, it's a t of this x1 dot xn. So then what we can write is t as t. I mean, let me just denote it as t. T is like x1, x2 dot xn. So it is a function of any function you can define, okay, which is free from theta. I mean, theta has no role here. I'm just, let's say x1 square plus x2 square. X1, the density of x1 and x2 could be like this function. There is a theta. But here, when I'm defining this t, this is a function only depends on capital X1, capital. So it is just any function of x1, x2, xn, capital X to capital X to capital X. Okay. So it is independent, free from theta, let's say. Okay. Okay. So, and we have seen that this is a remark, let's say, what we have observed that if the PDF, let's say, let me write it like this. So if the distribution of PDF of capital X is known, this is known, then possibly, okay, I mean, may not be it is possible always, because if t is a function of, I mean, a very complicated function, let's say, then is known, then, okay, the PDF or CDF, whatever it is, CDF of, let's say, t, okay, the statistic, okay, can be, we'll assume this can be, but it need not be, okay, because if xt is very, very complicated, it can be understood or can be analyzed or can be, let's say, can be, yeah, lengths can be analyzed, okay, can be found out, let's say, can be found out, okay, but we do not know this. Okay. And this t we are talking about, this PDF, so this is now I'm defining a new term, which is called sampling distribution. Sampling distribution. What is sampling distribution? The distribution of this t, the function t, is called the sampling distribution. What is the sampling? So t is a function of the samples, and distribution of t is called the sampling distribution. Okay, for example, if I say, what is the PDF of x1 square plus x2 square? Okay, so this x1 square plus x2 square is a function of x1, x2, okay, which is like t here. So the distribution of x1 square plus x2 square is a sampling distribution. Okay, sampling distribution is nothing but is the distribution, is the probability distribution. We can call it about CDF, probability, or PDF, whatever. So that's why I'm just writing probability distribution. Distribution, okay, of the statistic, t. So that is what is called a sampling distribution. Okay. Now, what is the distribution of the sample? So there is a difference. Okay, this is a function of this x1, xn. Okay. But what is the distribution of the sample? I mean, whenever you have a pair of random numbers like x1, I'm not pair, but a tuple of random variables, x1, x2, xn. So the distribution of the sample is a joint density, is a joint distribution, is the joint distribution, joint density function, let's say. So what we can say is like it is f, and there are parameters x1, small x1 corresponding to capital X1, small x2 corresponding to capital X2, and so on. And there is a parameter of course theta, because they're all individually distributed. So this joint distribution is nothing but the product of individual distribution, because they're all independent. You can call it like x1 theta, f of x2 theta, and so on. F of xn theta. So this is a product of I equal to 1 to n, f of xi and theta. Okay. Because the joint is nothing but the product of the marginals, because they are IID. Because x1 dot xn are it is. Okay. So now what we'll do is, so this is the joint disposal sample. Okay, so this is different from sample and distribution. Now what we'll do now, okay, we'll talk about sampling distribution. Okay, when this xi's have specific distribution, in fact, if this x, the population, okay, x, the population random variable, if x is normal, then what happens to different sampling distributions? That we'll talk about now. Okay. So our focus is now, to investigate sampling distributions, but we'll also study other distributions, and capital X is like other kind of distribution, sampling distributions, but this is our focus. Okay, when the population distribution is normal, and the population distribution, that's not PDF of capital X distribution is normal. Let's see. This is what we'll do. And there are three fundamental distributions. I mean, there are three fundamental sampling distribution, I will say. So one is chi-square. I'll talk about what, I mean, chi-square we already discussed, but I'll just make a reference. I'll not discuss much. And then we'll talk about students T distribution, the students T distribution, and another is the F distribution. These are the three sampling distributions I'll talk about. So these are nothing but some, I mean, I could have talked about these distributions when I did some specific continuous random variables, okay? But here, there is a certain context, so that's why I skipped there. So now we'll talk about it here, okay? So if we just remember what was chi, let us first talk about chi-square, okay? Chi-square. And then I'll say why it is a sampling distribution. I'll talk about that. But if you recall what is chi-square distribution, I said, like, suppose if I have a random variable x is a random variable, okay? Then if the PDF is like this, then we say it is a chi-square. XR, in fact, last time I think I defined just f of r because x is anyway variable. So this is, I mean, it is in the lecture 9. Okay, if you watch the video, it is there in lecture 9. So this is gamma r by 2 to the power r by 2. Same thing I'm defining it here. X to the power r by 2 minus 1 e to the power minus x by 2. If this is the function, this is how it is defined when x is positive or non-negative and 0 otherwise. So this is my chi-square distribution, and here we assume that I is bigger than 0, and R is called the degrees of freedom. And we also said, like, we denote it as chi-square R with R degrees of freedom. And we also discussed when we defined this chi-square that gamma square, okay, I mean, chi-square can be obtained from gamma distribution, the gamma distribution, okay? So, I mean, you have two parameters for gamma distribution, and if you fix those parameters certain values, I think there are alpha and theta. If you fix alpha equal to r by 2 and theta equal to 2, then you will get the chi-square. So chi-square distribution is a special distribution of gamma distribution, and the mean of x, mu of x was r, and the variance of x, I think it was 2 times r, but just check. I forgot. Anyway, so this is what is called chi-square. And chi-square also relate to normal. When you say this, also we talked about, when you take this degrees of freedom very, very large, then it becomes normal. So basically, so if you draw this, okay, because 0 to infinity only it is taking some non-zero value, otherwise it is 0. So this is in the positive axis. So if you say, let's say r equal to 1, so you'll get something like this. R equal to, let's say, 2, we'll get something like this. It will go close to 0. And then if you take r equal, let's say this is r equal to 3, then you say r equal to let's say 3. This is 2. This is 3. So you'll get something like this. And gradually it becomes normal when r is very large. Okay, so this is the picture. I mean, I may be wrong. I mean, we just have to plot it. Okay, so it will look like this. Okay, so from r equal to 1, we can see, I mean, what is the function. If you put just r equal to 1, you see what is happening. It's like this will be the dominant, this will play the dominant role. Okay, so and then you'll see. So r equal to 1, 2, 3, dot, dot, dot. If you take r very large, then it will become normal. Okay, so let me just make a remark. If this we talked about also before. So if r is large, so r goes to infinity, then okay, chi-square r, okay, is normal. Okay, so yeah. Now why? So what is the important thing about this? Why I'm calling it a sampler distribution? These also we've discussed before. But let me just recall in the sense of, in terms of sampling distribution, in terms of this statistic T. Okay, so this result we discussed before. So what you said is, if x is normal, mu sigma square, then we said x minus mu by sigma whole square, okay, is chi-square 1. This we discussed and proved before. Now see, this is a statistic. If you take n to be equal to 1, for example, okay, x1, x2, xn, sampler distribution. If you take this n to be equal to 1, then it is just a function of x or x1. Okay, so what is the function here? The function here is x minus mu by sigma. Mu is a constant, arbitrary or fixed. Sigma is a constant, arbitrary fixed. You can assume like this. So this is a function of capital X. Distribution of this is chi-square, 1 degree of freedom. So the standardized square of the standardized version of x, when x is normal, is chi-square with 1 degree of freedom. So chi-square is a sampling distribution. What is a sampling distribution? Okay, a distribution is called, same distribution is a probability distribution. So there is a random variable. So random variable is this one. So the distribution is called sampling distribution if it is a function of the sample random variables. So here, if you take n equal to 1, x itself is a sample random variable. So you have only one sample, and then it is a function, and then the distribution is chi-square. So chi-square is sampling distribution. We also proved this, the second result. Okay, so we proved it before. So that if x is, that's a normal, mu sigma square, and x1, x2, xn. I mean, we did not study it in this language, but I'll just state the result. Then you'll see that we have studied this before. And let's say x1, x2, xn is a random sample. Okay, from a population X, So that means the population is normal. Okay, and x1, x2, xn is the random sample. Then this also we proved before that xi minus mu sigma whole square I equal to 1 to n is chi-square n. We did not prove this in this language, but what we proved actually, that if we have sum of chi-square, this is basically sum of chi-square, because this is, you see from the previous result, it is chi-square with 1 degree of freedom. So this is chi-square with 1 degree of freedom, and n times we are summing it up, then only this get affected. It remains chi-square, and degree of freedom becomes n, which is the number of times you added the chi-square. So we proved it in a sense that we proved it that when you take the sum of chi-square random variables, okay, then you get back chi-square, and the degree of degrees of freedom of the new chi-square is nothing but the sum of the degrees of freedom of all the chi-squares which are involved in your sum. So this is exactly the same thing. So it is just a consequence of that. But here it has a different meaning now, because chi-square is now a sampling distribution, because you have a random sample, because they are all IID. So this sum in the left, they are all also sum of some independent random variables, independent chi-squares, let's say. Then the sum is again chi-square. So chi-square is just a sampling distribution. Only the n is coming from that these are all 1 degrees of freedom, all this xi minus mu by sigma, which you proved, which you stated in the previous stage. Okay, so that's why chi-square is again a sampling distribution. Another result, okay, which we also discussed, or which you'll follow from here, there's a second result, that if x is normal mu sigma square and x1, x2, xn is a random sample, the random sample from the population, okay, x, then n minus 1 s square by sigma square is chi-square n minus 1. Can anybody tell me why this is true now? Because see, s square is nothing but this, not exactly this, but xi minus mu whole square by n minus 1. So n minus 1 go up here, sigma square divided here, and then this entire term is nothing but chi-square because of the above related. But this is n chi-square, n minus 1. Now the question is, why these are important results when you do the data analysis or when you do the random sample? See, what was our idea? So we want to say something about the population mean, population variance through some statistic, some random sample. So from the random sample, we define what is called statistic. This is the function of the sample random variable. And if we know the distribution of this kind of functions, okay, this will help me. So depending on the application, where we need to, let's say, find out this one. Okay, x1, we'll see some example, let's say. But so suppose we need to know this. What is this? Okay. So then, since this is following a standard distribution chi-square, we have the chi-square table, and we can easily find out probabilities associated with this statistic. Okay, probabilities of events which are associated with this statistic. Okay, let us first see an example. Okay, example. Let's say x is normal. Say 10, 25. So 25 is the variance, 10 is the mean. And let's say you take a large sample. Let's say I say x1, x2, ... some 501 samples. Okay, I have chosen this from the population of x. The question is, my question is, I want to find out what is the expected value, okay, or the mean of the sample variance. What is this? Who can tell me this? I want to use the above results. See, S square is here. So can anybody tell me now? So I do not know exactly the distribution of S square, but I know the distribution of n minus 1 S square by sigma square. All right. So what I know here is, yeah, can anybody tell me?
Yes, I think it should be sigma square.
Okay, let us see. So from the above result, what we know is that n minus 1, that means 501 minus 1 times S square by sigma square. What is sigma square here? Anyway, right? Let us write it. S square is a chi-square 500, right? Because it is n minus 1. You see, n minus 1. It's 500. Now, what we want to find out? We want to find out the expectation of S square. We know this is the distribution. So basically, this is expectation because I want to use this. So it is as 500 by sigma square is 25. Anyway, so you can write 25 by 500 times 500 by 25 because I know this distribution of this part, which is the chi-square, 500 by 25. So I multiplied this because this was a square. So here I multiplied this 25 and 500 in the denominator, so that this 500, 500, 25, 200 get cancelled. This now it is expectation of some scalar, let's say alpha times the random variable here. Now then what is that? Alpha will come out because this is a linear operator, a linear transform as you have studied in math too. So this is alpha. Alpha means here 25 by 500. So alpha will come out, and then expectation of 500 by 25 square. Now this I know that this is, so this is 25 by 500. Alpha should be equal to what? 420. So 1 by 20 times expectation of chi-square 500. Now what is chi-square expectation of chi-square 500? Huh?
500.
Yes, 500. Because we just said it here. Okay. I mean, we said it before also, but here also we said today. See, the mu expectation is R when it is chi-square R with R degrees of freedom. So we know. So it is 500 degrees of freedom. So it is 1 by 20 times 500, so which is 25. This is exactly the variance. Otherwise, directly also you could have said it's variance, but anyway, so let us just, okay, the calculation. So using this, we can say this one. Okay. Now what happens in the exam situation? In the exam situation, so this will not be, let's say, given to you. Okay. So suppose you are asked to find out, okay, there is a phenomena given to you in the question, and this phenomena, let's say some mean and variance is given to you. Let's say how many times like the number of minutes you take from this for the exam, for the tests, let's say for all the students it's normally distributed, something like this, and there are 500 students. Okay, so these are all independent. So then this becomes all independent random variables which are normal, and then you will be asked to find, okay, what is this in terms of a square? It can be stated in terms of English language. Let's say the distance from the mean minus this xi square. Let's say xi is the time taken by ith student minus mu, and square of that is something. Okay, as that is what you have to find out, something like this. So basically that it will be in disguise probably, or maybe it could be direct, just direct. So since you know this distribution, so this is the way class. I mean, in a class situation, I mean, class means in an exam-like situation. Okay, for this course, this is like important in a sense, like you know this distribution. So basically, you have to find out how to solve some problem using the fact that this is following chi-square. Okay, it's something like this. It is not a big deal. Okay, now let us discuss what is called students T distribution. Students T distribution. So this is a new sampling distribution. I mean, it is a distribution, but it will observe this as a sampling distribution. That means, so it will be observed, or it can be, this distribution can be obtained as a distribution of a random sample, okay, or associated with a random sample, or with the statistic that could associated with a random sample. So distribution. So you can independently treat it as a distribution function as a random variable, does not matter. Okay, I mean, this is a distribution corresponding to some random variable, but we are calling it a sampling distribution because it can be seen, like the way chi-square we have obtained, it can be seen as a distribution of a statistic, okay, for some random sample. Anyway, so let us first define what is the PDF here. Okay, so this is a continuous distribution. So this is a distribution for continuous random variable, for continuous random variable. I mean, you can see the domain. From the domain it will be clear, but still let me just write it. Continuous random variable. Okay, and this is how the PDF is defined. Let's say X with PDF. This is the PDF. If you have X, which is the variable, and the parameter is, see, now every time I am writing this parameter now. Earlier I wrote R as the parameter, and there is a reason to it. Earlier I did not define it like this way. Okay, there is a reason. So I'm denoting it like FC here, F R X, this semicolon R. Earlier, if you go to my lecture number 9, you'll see that I just said F of R because X is already given here. Okay, but here now I am saying both X and R. Similarly, here I am writing X semicolon this some new. So this is called new. This standard notation new. Greek letter new. So like n, okay, so new. So why I'm saying this, because say here, when I started talking about this discussion about the sampling distribution, I said x has certain distribution in x and theta. There is a parameter, let's say theta, and 1 or 2, 3, whatever the parameters are, and they are all distribution. Let's say some they have some general distribution, and the parameter is theta. And the same way I'm trying to write it, f of x and theta. Why I'm writing, there is a reason. The reason is, I'll discuss this later. Reason is, I mean, not today, but next day, is that sometimes you know, suppose it is normal, but you exactly do not know what is the mean and variance. You have a guess about the distribution, but you do not know the parameters of the distribution. Then you have to estimate the parameters. And that is a problem of estimation. Okay, we'll talk about that later. But I'm just telling you why I'm denoting this PDF as this f x comma theta or x semicolon theta, because theta will play a role in our next class. Okay. Later on, we'll see why. Suppose there is some process. Okay, something is obtained. Okay, in a population is created. Okay, by measuring something about something. Okay, and this we know that due to the procedure, the way it is produced, from there we have a guess that it is, let's say, exponential. It's let's say Poisson. It's let's say normal. It's gamma. Whatever it is. Okay, we have a guess, but we do not know exactly what the parameters are. We have a guess about the distribution, but we do not know the parameters are. So then the question will be, from this population or from a sample, can I estimate the value of the parameter or the values of the parameters? That's why I'm writing it in this way. Okay, so there is a difference. So when we discussed about the PDF, we just said it's a. I mean, I would have written this is f of new, but right now I am writing f of x semicolon new, just to stress that new is the parameter which is involved with my sample or with my population. Okay. Yeah. So how this is defined? This is defined like this: gamma new plus 1. Okay. Sometimes I write like this, or new plus 1. In fact, it is not exactly new, but anyway, let us say whatever it is. 2. Okay. Yeah. Then here it is pi times new, then gamma gamma of this by 2, okay, and this 1 of 1 plus x square by new to the power new plus 1 by 2. Okay, this is the entire thing to the power, and this is defined when x could be anything. And new is the parameter which is bigger than 0. So when you say that x has what is called T distribution with degrees of freedom, or with new degrees of freedom, and we denote it like x is distribution at T new. This is the parameter. This is the notation. Now this is called student distribution because of something. Okay, so there was a guy. Okay, there was you can say mathematician or an engineer. So his name is, just it is a little bit of history. Why is it called student distribution? So this guy's name is Gossett. Okay, he lived physically in this world, I think 76 to 1936. So he was working in a company. Okay, but and also parallelly he was working on something. Okay, some mathematics, some data, but it was not allowed by the company. I think that is a true story, but I'm not sure how much true it is. But I mean, this is what is a popular story about this distribution, that he used to work in a company. I mean, it was in England. Okay, in England. This time we are fighting for our independence, but anyway. So he is a British. Anyway, so he was working for a company, and but company did not allow him to publish his work. So what he did is he used a pseudonym called Student, okay, who published his work under the pseudonym of Student. Okay, so like when he was publishing, so suppose you publish some article, scientific article, some investigation you have done, then you have to give who is the author, no? So instead of his name, he used the pseudonym Student, and that's why it is popular as student distribution. Okay, this is nothing about nothing. This is nothing about like students use it. That's why it is called student distribution. It's not like that. Okay, so because this guy used the pseudonym Student, so that's why it's called student T distribution. Okay, but you can say, I mean, this is a very complicated thing. I mean, okay, I mean, you can define your own function, and you can show that if you are able to show. Suppose you do a lot of data analysis for 5 years or 1 year or whatever year. Okay, and you found out that okay, if this I mean somehow suppose we prove that there is a sample, I mean there is a sample and distribution which is following, let's say, some kind of special kind of function which has a compact analytical form like this. It could be complicated, but it has a nice form. It has a formula. Okay, then probably you can treat this as you can write an article and you can write that this is the sample distribution of some kind of random samples. When the random samples have some kind of a distribution, then this can be obtained as a sampling distribution. This is, I mean, this is sometimes this kind of thing. Okay, this kind of thing, like getting an analytical formula is hard, is difficult. It's not very simple. I mean, this function looks like very simple, but how it is obtained, it could be a very tedious method. I mean, after observing a lot of data, this and that, this is somehow he got this idea that it can be expanded like this. It can be expressed like this. Okay, so it is not a cool job. I mean, it could be a very tedious job. But anyway, so then you can write an article. Okay, so since like that. So, okay, but this distribution, although this is complicated, but it can be shown that this distribution is a generalization of Cauchy and normal. That means for some specific values of this nu, okay, you can get the standard distribution, which you already know. For example, if nu is equal to 1, what do you get? F of x1 is what? See, let us see. Is here it is gamma 1. What is value of gamma 1 if you put nu equal to 1? What is gamma half? Here also gamma 1. Oh, not gamma 1, but it is just 1. Gamma equal to 1. And here it is 1. So only just root pi. Who can tell me what is gamma of 1? Who put gamma, this nu is equal to 1.
It is 1.
It is 1. And here it is gamma half.
Under root pi.
Under root pi. So under root pi, here under root pi, so this will be pi. Here it is 1 by plus x square. So basically it is 1 by pi times 1 plus x square. Yeah, very simple. Okay, so this is a generalization. This function is very, very complicated. But if you pick different values of this nu, okay, you will get some special kind of distributions. Okay, so like this, like you get Cauchy. This is Cauchy. We talked about this in this course. Cauchy distribution. Okay, now if you take nu very large, okay, then it can be shown. I'm not proving it. Then it can be shown. Then the limit of nu goes to infinity. F of x nu is nothing but 1 by 2 pi e to the power minus half x square. So it is standard normal. Okay. So basically, what does this mean? This means if you want to plot this, okay, because it is defined for both minus and infinity. If you plot this, so if you go, so that's why I don't want to plot this things, because it will look like similar to normal, but it is kind of a different, totally different distribution. So it will go like this, and when it is normal, is gamma, this value, let's say it is nu equal to something like 1, 2, something like this. And then if it's very large, nu is very large, then it will be approximately normal. Let's say this is gamma tends to, this is nu tends to infinity, let's say. So then it is like a normal. Okay, so this is what it means. Okay, so let us solve some problem. And you have a table for t distribution. Okay, before that, let me just tell you what is the expected value of this random variable x, which is t distribution. This is 0 if nu is bigger or equal to 2, and because nu is the degree of freedom, its value is integer, so there is only one value left, nu equal to 1, and for nu equal to 1, this does not exist. Expected value does not exist. Okay, if nu is equal to 1, and the variance of this distribution or this random variable is nu by nu minus 2 if nu is bigger or equal to 3, otherwise it does not exist. It does not exist if nu is equal to 1, 2. Now I'll justify why this is called a sampling distribution. Okay, so this is just a distribution. Okay, now why it is called a sampling distribution? Okay, so this is my result. If let's say z is normal, standard normal, and u is another random variable, is chi-square some nu. Okay, that means chi-square with nu degrees of freedom, and z and u are independent. So what is happening? Z and u are independent. So you have a random sample, let's say x1, x2. X1 is z1. So the way x1 is opened, it is following normal, but x2, let's say u, is chi-square. But chi-square is also associated with standard normal. Okay, remember that. So basically, chi-square nu means what? Is the sum of, you can say, new number of chi-squares. Okay, this is what we proved earlier. Okay, and each chi-square is again coming from standard normal. Okay, or from standard normal you can get the chi-square. So this is standardizing it. You see here we talked about it. So these are not completely unrelated. So I am not writing it the entire thing, but I'm just saying, yeah, see here chi-square 1 can be obtained from normal, the standard normal. So square of the standard normal is chi-square. Okay, so I'm just saying that z and u, there are two random variables. First one is standard normal. Second one is the square, sum of the squares of standard normal, meaning it is, let's say, chi-square nu. Okay, so and let's say they are independent. Then if you define this statistic w, which is z divided by square root of u by nu. Nu is that number, degrees of freedom. This is t distribution with nu degrees of freedom. So then this becomes a sampling distribution. So you have two samples here, u and z. Let's say z or z is standard normal and u is chi-square with nu degrees of freedom. And this statistic, this is a statistic now, w. And this statistic is t distribution with nu degrees of freedom. Okay, I'm not proving it, but this is what it is, the result. I'm not proving, you can easily prove this, that's why I'm not proving it. Another result, which is important, which I'll prove, is if x is normal, sigma square, and let's say x1, x2, dot, 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 xn is a random sample. Sample from the normal population, from the population x, then x bar minus mu by s by square root of n. This is t with n minus 1, and this I'll prove. X bar minus mu divided by s. What is s? This is the sample standard deviation, square root of s square, s by root n. So this becomes a statistic now, and this statistic is having t distribution. Okay, we'll take 3-4 minutes break and then we'll start again. Okay, let us take 2-3 minutes break. Yeah. So Let us prove this. The proof is very simple. Okay, let us prove this. Now, what we know here is x1, x2, xn, they are all standard normal. Normal mu sigma square, and they are IID. So what can you, so because my focus is to find out this, I want to first find out what is distribution of x bar. Who can tell me? If they are normal IID, what is the distribution of x bar? Remember that x bar is nothing but a linear combination of special linear combination of the normal. We talked about this. I mean, if you have actually any distribution, and if we take a linear combination of those, and they're all IIDs, then we know the mean and variance. For normal, it is very, very special because we know the distribution as well, along with mean and variance. So what is that? X bar? X bar is nothing but
normal
yes, normal
of mu by n and sigma square.
No, it was just mu. It was just mu. Because n times this expectation, if you take, it's an expectation linear function. So n times mu by n, which will be n. So which will be mu. And this sigma square by n. So we know this x bar. But if I know x bar, and this is the normal, then we know x bar minus mu by square root of the variance, which is sigma by root n. And this is what?
Standard normal.
Standard normal, yeah. See, almost we are reaching here. Only except the fact that it is S. Okay, reaching here. Now, if something is standard normal, we know the square of it. In fact, okay, if you have standard normal, what is the square of it? We take the square of it.
Chi square.
Yes, chi square is 1 degree of freedom. But we have proved more than that. Say here, I mean, at least we have stated and I discussed how to prove. You see here, n minus 1 times s square by sigma square is chi square when x is standard normal. Okay, so from here, what can you say? It is also standard normal. It is also normal, but it is specifically standard normal. So mu is 0, sigma is 1. So n minus 1 s square by sigma square is chi square n minus 1. Okay. Now this is chi square by 1. Then what happens? X minus x bar minus mu by s by root n. This will be what? X bar minus mu by sigma by root n divided by square. You can write this as n minus 1 s square by n minus 1 sigma square. Now what is this? This is normal. This is chi square. Here, this result. Z is normal, standard normal, and U is chi square mu. If you take Z by square root of U by this nu, this is T of T distribution of this. So this will be T of n minus 1. This is the proof. Now I must tell you, see, lastly also I said that you have too many information here. And all these distributions are actually connected to each other using some function, some statistic. Okay. So you should prepare for the exam, at least you should prepare a cheat sheet where you should have the idea of, I mean, it should be written like you can immediately see how the distributions are connected to each other. Okay. In fact, if you type it in Google, the cheat sheet for statistical distributions, you'll get this kind of cheat sheets. Okay. That where it is mentioned how all the distributions are connected to each other, which follows what. Okay. So that should be with you. I mean, when you are solving this kind of problems, because here you have this facility of online. Okay, if it is offline, then you have to remember it, which has no meaning. But anyway, this is how our academic system works, which is not good. You have to understand this. but we have limitations. But anyway, what to do? I mean, anyway, so I mean, if you say less, then it is good. You should not say more about it. Anyway, so at least you should have a cheat sheet ready, like how these distributions are connected, okay? And then you can solve some problems, okay? Okay, let us see. Let us solve a problem. So let us say, suppose I have 4 random variables, x1, x3, x3, x1, x2, x3, x4, okay? Suppose this is a random sample. It's of size 4, the random sample. Okay, from X, which is standard normal. So N01. Now I give you a statistic. So this is my question. Let's say my W, I'm defining it to be x1 minus x2 plus x3 divided by square root of x1 square plus x2 square plus x3 square plus x4 square. My question is, expected value of this is what? Okay, so again, I'm saying, I mean, iteratively, I'm saying, because all these things may seem meaningless. Why I'm doing this? Okay, just to pass an exam or what? Okay, so truly speaking, if you encounter a data set in real life, okay, or in a project, let's say you are doing a project, okay, so if you model the problem, this kind of functions will appear, okay, like you have a random sample and you want to find something about the data where the corresponding statistic is actually this. I mean, this is a function. So you will get a function, okay? And then you have to find some value of this statistic. That's how what we are doing in the training process, like in the classroom situation, we are defining some kind of complicated functions. We are trying to tell you that, okay, if the function is this, then using the techniques which we discussed, okay, how you can find it. And here the basic assumption that you know already the population distribution. So how it is known? Because the way it is produced, it is known to you, and that's how you have a guess. That's why this is standard normal. Okay. So if you know this, then we have to find the expected value of this statistic. Now, who can tell me how to do it? Okay, let us see. So xi is or x1, x2, these are standard normal. This is given to me. Now it is it's a ratio of two distributions. Okay. So let us first see what is about the numerator, and then we talk about the denominator possibly, or maybe whatever the results we know, where there is a ratio of something which we have done today. For example, t distribution, we have seen this ratio, okay, this ratio or this ratio, okay, this ratio. So probably we have to use it. This is the guess. So xi is 9. Now what is the numerator, distribution of the numerator? x1 minus x2 plus x3. This is the numerator. Okay, what is the distribution? You can tell me. Again, it is a linear sum of independent normal. So what is this? This should be normal, of course. We said it before also. Now, what is the mu and what is sigma square? These are all standard normal, x1, x2, x3. Here, instead of x1 plus x2 plus x3, I have x1. But anyway, it is a linear sum. So what is that? What is the mean? And what is the variance? So before we said, like if you have any linear combination, you can do that. So if you have any linear combination, let's say a1x plus x, a2x plus a3x3, a1 x1 plus a2x2 plus a3x3, we know the mean. What was the mean? Here the
That will be 0.
Yeah, 0. And then what is the variance? To look at the formula, that if you have a linear sum of independent random variables, okay, then we can easily find the variance. So all these formulas, okay, should be with your hand actually when you are appearing for the exam. So this will be 3. Okay, you can check it later. This is 3. So if this is 3, then yeah, x1, x2 plus x3 by root 3. What is this? This is what?
Standard normal.
Standard normal, yes. Because this minus this entire thing minus 0 by square root of the variance, which is root 3, standard normal, standardized version of this. Okay. This is one thing. Now here you have square of this, square of standard normal. You already know what is the distribution of square of standard normal, which is chi-square, right? Now, this is one part. Another part is xi is a normal. So xi square is what? Xi square will be what? Xi is normal, so xi square. Today also you said this. Normal?
Standard normal.
No, xi is standard normal. So what about xi square? Today also you said this.
I square.
Yes, chi-square 1 degree of freedom. Now if xi square is chi-square, then what about x1 square plus x2 square plus x3 square plus x4 square? Sum of the squares of normal standard normal is what? The sum of squares of chi-square is what? Independent chi-square. Yeah, this is chi-square.
I-square
4. Yeah. Then we have this chi-square 4, and here with this we have normal. And the intended one, the desired one is the this ratio of these two, which you already have seen here. Okay, which you already have seen here. So this implies then, okay, x1 minus x2 plus x3 by root 3 is standard normal divided by the square of it, x1 square plus x2 square plus x3 square by square root of n. Yeah, so it is 4. So this is 2 by 3, 2 by root 3. Root will come down here. This is t distribution. Right? This will get some w, which is t of 4. So then, what I have to find out is expectation of w, because w is the required one. W is the required one. So this will be expected value of root 3 by 2 times 2 by root 3 times w, which is root 3 by 2, the same trick which we used earlier. Equation of t of 4. Example of t of 4 is what? This we also said here, t distribution, we talked about the expected value, which is 0, you see. Now when you define this, yeah, see here, expected value is 0 when gamma is, nu is bigger or equal to 2. Okay, so here it is 4, so it is 0. Then 0, which is equal to 0. Okay. Okay, another problem. Let's say I have x, which is standard normal, and let's say I have two random sample of size 2. Okay, and suppose x1 I have 2 random sample. Random sample of size 2, which is IID. Okay, distributed as x. Now the question is, what is 75th? Not percentage. 75th percentile of W, this statistic, which is x1 by square root of x2 square. This is the question. So do not, get afraid looking at a complicated question like this. Okay, just relax. We have all the methodologies to answer this. Okay, so just you have to remember everything. So x1 is what? X1 is normal, standard normal, and x1, x2 square is what? X2 is also standard normal, so x2 square is chi square. 1. Then what is W? This is a ratio of these two. We have also seen, so x1 by square root square is now T distribution with 1. We have seen that. Now, what is the 75th percentile? Then, if you remember the definition of the 75th percentile, let's say A of W. This is the value. That means 0.75 is equal to probability of W is equal to A. Right now, from the table, now you have to look at the table of T distribution. And for what value of A, you will see that this probability is 75. So that you can see from the table. So from the table of T distribution, A will be equal to 1.0. So that's the answer. So just you have to find that this is T distribution is 1 degrees of freedom. And then we have to use the table that for what values of this A, this is 0.75. That's it. Okay. Yeah. Now we'll define the last sampling distribution for this course is F distribution. F distribution. So this F, okay, I mean this F is important. This is a little complicated, but this is a good distribution when you do a lot of statistical data analysis. Okay. Okay, we'll see some application later on. Let's suppose the PDF. So X is a random variable. Then X has F distribution if the PDF is this. So there are two parameters now. Instead of one, there are two parameters. This is much more complicated than the other one, the T distribution. So this is X, mu1 and mu2. Okay, so this is like this. Gamma of mu1 plus mu2 by 2. Then mu1 by mu2 to the power mu1 by 2. Then x to the power mu1 by 2 minus 1 divided by gamma of mu1 by 2 gamma times gamma of mu2 by 2 times 1 plus mu1 by mu2 times x to the power gamma, I mean mu1 plus mu2 by 2 when if 0 less equal to x less than infinity and 0 otherwise. So this is a little complicated, but doesn't matter. And this with just the mu1 and mu2, these are positive. Okay. Then we'll say that X has F distribution with mu1 and mu2 degrees of freedom. Degrees of freedom. And we denote X is distributed as F of mu1. The little bit history about this F. F stands for, there's a guy called Fisher. So his name is Sir Ronald Fisher. He is also a very well-known statistician or information theorist. There's a concept called Fisher information. If you study digital communication systems or information theory in general, then you'll see there's something called Fisher distribution. So this was not invented by him, but it's invented by somebody called George Snedeker. Okay, and he named this distribution after Fisher's name, and that's why you call Fisher distribution or F distribution. Okay. So okay, so this distribution is, let's say, named after this F stands for Fisher here. Okay, Fisher. Now, so you'll see why we are doing this. So if you take ratio of variances, then this will be an important distribution. And if both this gamma 1, this nu 1 and nu 2, or gamma 1, gamma 2, whatever it is, if they are very large, both are going to infinity, okay, then this distribution becomes normal. I'm not just proving this or anything. I'm just making a statement, okay, which can be proved, but it is out of the scope of this course. So if nu 1, nu 2 are very, very large, then this will give you the normal distribution, okay. The first observation, okay, let me just say, what is the expected value of this? Expected value is nu 2 by nu 2 minus 2. If this nu 2 is bigger or equal to 3, otherwise it is does not exist. Does not exist. It does not exist if nu 2 equal to 1, 2. Because they are degrees of freedom, so they are positive integers. And the variance of this x is, this is a little complicated formula, 2 nu 2 square nu 1 plus nu 2 minus 2 by nu 1 nu 2 minus 2 square nu 2 minus 4. They're all complicated. If nu 2 is bigger or equal to 5, whatever be the value of nu 1 doesn't matter. Otherwise, it does not exist. Does not exist. It does not exist if gamma 2 or nu 2 is 1, 2, 3, 4. Okay. Now, again, it can be shown that this result will not prove it, but we'll make a statement here. First statement is, if x is F distribution with parameters nu 1, nu 2, then 1 by x. So x is positive, let's say, or at least non-zero. 1 by x, so that 1 by x is defined. This is F nu 2, nu 1. So all the formulas, whatever we have derived, so I mean not derived but mentioned, just expectation or variance. Nu 1 will be replaced by nu 2, nu 2 is replaced by nu 1. Okay. Okay, so this is one important thing to. Okay, another thing is, okay, let me get another result. Another result is, if we have some random variable u, which is chi-square with some nu 1, and some v, which is, let's say, chi-square nu 2. So these are all chi-square with nu 1 and nu 2 random variables, and let's say u and v are independent. Then the ratio of this u by nu 1 divided by v by nu 2. So the ratio of chi-square is f. Is f with nu 1. This is an important thing to remember or mention. Okay, we will not prove this. Okay, proof is similar way, like all. I mean, you have to write it down like all these things, and like u, v, and all the standard results, and then you have to show that, okay, this is f, but it would be long. Okay, let us see some problems. Okay, now suppose I have two random samples. Suppose we have two random samples. Instead of one random sample, I have two random samples. One is, let's say, x1, x2, x3, x4. And another one, let's say, y1, y2, y3, y4, y5. Okay, and the population distribution is less than normal from X, let's say, which is standard normal. Okay, the question here is, what is the variance? Just say variance of t is equal to what? T is the statistic here, where t is like this: 5/4 times, that's x1 square plus x2 square plus x3 square plus x4 square. Here is y1 square plus y2 square plus y3 square plus y4 square plus y5 square. Now see here, this PDF, whatever complicated it is, it does not actually matter to us. Even if you do not know this, but you know the statistical table of this and all these results which connect other distributions, then you can solve some problems. Okay. So if you just know the mean, variance, and whatever the distribution is, don't care, but know the connections with other like these two results, then you can solve some problems. Okay, so let us say what is the solution here. Can anybody tell me? Okay, let us first consider the numerator of this t, the statistic t. X1 square plus x2 square plus x3 square plus x4 square. What is its distribution? See, xi's are all normal. So what is this distribution?
chi-square 4.
Yes, chi-square 4. Now let us talk about the denominator part. Y1 square, this is y1. Y1 square plus y2 square plus y3 square plus y4 square plus y5 square. What is the distribution here?
chi-square 5.
Yeah, chi-square 5. They're all independent. Some of squares are normal, standard normal. So this is chi-square. Now what I asked to find, t is equal to 5/4 times this. Okay, or you can write it like x1 square. Now see, I want to use this formula. So this chi-square by chi-square. So chi-square divided by nu1, nu is the degree of freedom, and this in the denominator part, chi-square divided by nu2, which is the degrees of freedom. Basically, you have to make it like this. Here the degree of this one is 4. Here it is 5. So x1 square plus x2 square, x square plus x4 square divided by 4 divided by y1 square plus y2 square plus y3 square plus y4 square plus y5 square divided by 5. So this is my t. Okay, so I can get rid of this. So this is t, which I know that this is f45 from the above result. Now from the statistical table, or maybe here the question was variance actually. I don't have to find any, just a variance. So the variance of t is what? The variance of f of 4, 5. Now I can use the formula. Okay, a variance here. So gamma 2 is bigger or equal to 5. That means I have to use this. It is independent of gamma 1 or let's say mu1. And so I have to use this formula to find its variance. That's it. Done. I'll get some value. Another interesting part about F distribution is the following. This is again one more result. So I will try to prove this also. So, but because normal are very, very important. So I'm focusing on normal. Okay, X, let's say is normal. Let's say mu1 square, mu2 square. Sorry, sigma 1 square. Let's say. Sorry, mu1 sigma square, and let's say x1, x2 dot 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 xn. These are sample. Okay, sample random variables. IID with x. Okay, and let us say y is one more random variable, which is normally distributed mu2 sigma 2 square. Okay, and let's say another random sample I have y1 y2 dot dot dot. Let's say ym, which is IID of y. Now let us consider the statistic. Then this is what makes us, which makes F distribution important. Then the statistic, because F distribution can be seen as a ratio of sample variances corresponding to normal distribution, normal population. The statistic, this S1 square by sigma square divided by S2 square by sigma 2 square. This is F n minus 1 m minus 1. So what is happening here? I have two populations. One is corresponding to X and is corresponding to Y. Both are normal. I take a sample from X, take a sample from Y. For example, height and weight, X and Y, let's say. Height has certain distribution, weight has certain distribution, which are normal, let's say. I take a sample from height. So let's say n number of sample points. So all are IIDs, so they are all normal. And here I take Y, m number of this. Then if I take the status of the sample variance, the ratio of the sample variances, and that will be F distribution. And the proof is very, very simple. Anyway, so let us prove this. What is that? Xi is n mu1 sigma square. Then what we know, because I have to talk about sample variances. So just recall n minus 1 times S1 square by sigma square is equal to what? Today we discuss chi square n minus 1. Okay. We discuss this today, the third result about chi square. Where is that? Yeah. This is so many things we did today. Yeah, this one. This one I'm talking about. N minus 1 times S square by sigma square is chi square n minus 1 when X is normal, mu sigma square. Okay. So now I am applying this result here. Okay, so this is chi square minus 1. Similarly, m minus 1. Similarly, m minus 1 times S2 square by sigma 2 square is chi square m minus 1. So therefore, what we have is S1 square by sigma square divided by, this is a required. Okay, I want to show that this is F. Okay, so S2 square divided by sigma 2 square. This is, I can say, n minus 1 divided by n minus 1. S1 square by sigma square. Here n minus 1 times S2 square by n minus 1 sigma 2 square. And this is F. Why? Because the ratio of chi square, here I said, ratio of chi square is F. Here we said here. So chi square, U is chi square divided by its variance, its degrees of freedom. V is also chi square divided by its degrees of freedom. Then it is F. So here is F. So this is F n minus 1 m minus 1. So this result will also help us to solve certain problems. Okay. Yeah. So I mean, let me say that this is what I wanted to discuss about what is called sampling distribution. Okay, so now I am a little happy because the syllabus is now under my control. I mean, I am not revealing you what is the syllabus of the next class test, but at the syllabus is like next I have to define, I mean, according to our course curriculum, I have to discuss estimation of parameters and then testing of hypotheses, which are very, very important. Very, very important in a context that if you want to, you know, do a course in data analysis, or you want to, you know, do a project on statistical data analysis or something like that, then this will play a big role. Like the what is called this testing of hypothesis and estimation of parameters. I mean, this is actually what you have to do. So we'll discuss this next. But we have 15 minutes time. So let me have, I mean, let me have a chat with you. Okay. So how are you doing and this and that. So let me stop the recording here. And now we can do a little bit of chat. What are you doing, this and that, because I was always, I was always afraid whether I'll be able to complete the syllabus or not. But anyway, I'll be